Chemical Equilibrium, Part 3. We're going to take a look at the magnitude of KEQ and what that tells us about the reaction. We're going to take a look at the direction of the chemical equation and how that affects KEQ. And we're going to take a look at several aspects involving the stoichiometry of the reaction and KEQ. So to begin with, the magnitude of KEQ tells us something about the reaction. Let's consider this reaction as an example. CO and Cl2 are in an equilibrium with CoCl2. We could say that the Kc expression would be the concentration of CoCl2. Remember that since there's 1 mole of this would be raised to the first power. And then in the denominator, it would be the concentration of CO, because there's 1 mole here, that would be raised to the first power. And Cl2, because there's 1 mole here, that would be raised to the first power. So this is the equilibrium constant expression expressed with concentrations, Kc. Now notice that, in general, the equilibrium constant is equal to a product of the concentration of the products, or if we're dealing with pressures, a product of the partial pressures of the products raised to the appropriate powers, divided by the product, or the multiplication, of the concentration of the reactants. Or if we're dealing with pressure, it would be the pressure of the reactants. And that would be Kp if we had pressures involved. Notice that since it's product over reactants, if KEQ is very much bigger than 1, and if you're not familiar with this notation here, when you have 2 greater than signs, that means it's very much greater than. In other words, we have a large value for KEQ, much bigger than 1. Then the equilibrium would lie to the right. We'd have more products than we would have reactants for concentration or for pressures. So the products would predominate when equilibrium was established. The balance point would occur when the concentration of the products was much bigger than the concentration of the reactants. Now on the other hand, if we have KEQ that's very much less than 1, in other words, a small KEQ value, a decimal value, or small decimal value, then we could say the equilibrium lies to the left, and we have more reactants than we have products. The reactants predominate at the equilibrium state. That means that the values in the denominator would be bigger than the values in the numerator. And that's always going to be true. So the magnitude of KEQ can tell us where or when the equilibrium state is established, whether we'll have more products or more reactants. Again, KEQ bigger than 1 means more products, because the products are in the numerator. And KEQ less than 1 means that we'll have more reactants, because the reactants are in the denominator. And we would say products predominate in this situation, and reactants predominate in that situation. So let's take a look at the direction of a chemical reaction and KEQ. If we express this as our chemical equation, we could say that KEQ for the forward reaction, or Kc in terms of concentrations, would look like this. Now let's say that that's equal to 0.212 at 100 degrees Celsius. If we flip this around so that we have 2 NO2s written as reactants and N2O4 written as products, in other words, if we write that reaction in reverse, then the Kc for this equation is actually the inverse of that expression. It's the reciprocal. We flip it upside down, and we get the inverse of the numerical value. So instead of being 0.212, it's 1 over 0.212, and that calculates out to be 4.72 at 100 degrees Celsius. Now that's always going to be that way. If you take a reaction and flip it, we can say that the Kc ends up getting flipped, or we get the inverse or reciprocal. So KEQ for a forward reaction equals the reciprocal of KEQ for a reverse reaction. We could write that this way. Now let's take a look at some points involving the stoichiometry of reactions and how that affects KEQ. Let's stick with this reaction. And remember that we said Kc for this reaction at 100 degrees Celsius was 0.212. And remember that whenever you see a Kc established, because it's temperature dependent, we should identify what temperature that value corresponds to. So this is the general format of Kc. We're saying it's 0.212. What would happen if we would double the amount of reactants and double the amount of products? So we go from 1 mole and 2 moles to 2 moles and 4 moles. Well, now the Kc expression for this reaction would look like this. Concentration of NO2 to the 4th power, because that's a 4, and the concentration of N2O4 to the 2nd power, because that's a 2. So notice that if we take this Kc expression here and square it, we would get this, because 2 times 2 is 4, and 2 times 1 is 2. So the Kc for this reaction with double the amount of moles is equal to the Kc value from up here squared. So if we double the number of moles, we square the Kc value. And likewise, if we triple the number of moles, we would have to take the Kc value to the 3rd power. So we can say that, in general, the equilibrium constant for a reaction, and this could be KEQ as Kc or Kp if it were all gases. So if you multiply by a number that equals, KEQ for a reaction that has been multiplied by a number equals the KEQ for the original reaction raised to a power equal to that number. So the power of the multiple is involved there. Now another stoichiometric relationship has to do with reactions that have multiple steps, where you can add some reactions together to get a net reaction. And this is somewhat reminiscent of what we saw with Hess's law. So let's say we have this example where we have our first equation where 2 NOBRs are in equilibrium with 2 NOs and a BR2. And the equilibrium expression, or the Kc for that, would look like this. Concentration of NO squared, because we have a 2 there, and the concentration of BR2 to the 1st power, because we have a 1 there, divided by the concentration of NOBR raised to the 2nd power. Now that would equal 0.014 at 100 degrees Celsius. Let's say we have another reaction where we have BR2 and Cl2 in equilibrium with 2 BrCls. So the products divided by the reactants, and these are multiplied. So the concentration of BrCl2 to the 2nd power, and again that power is because of that number of moles, divided by Br2 concentration and Cl2 concentration. And let's say that's equal to 7.2 at 100 degrees Celsius. Now if we sum these two reactions, in other words, if we add up all the reactants and all the products and simplify, we get this equation right here. So we have 2 NOBRs and Cl2 producing 2 NOs and 2 BrCls. Notice that Br2 is a product here and a reactant here. So the Br2 ends up simplifying out of the equation. So now for this third equation, that's a net sum of these two equations, we get a Kc value that's equal to this. Notice that's the same as if you took this Kc for equation 1, and this Kc for equation 2, and multiplied them together. Then we'd see the concentration of the Br2s cancel out. So we can say that KEQ for a net reaction, in other words, a reaction that's a sum of other reactions, is the product of the KEQ values for the individual reactions. In other words, Kc for the third reaction, the net reaction, is equal to a product of Kc from the first reaction multiplied by Kc from the second reaction. Now numerically, 0.014 times 7.2 would give us 0.10. And since these are at 100 degrees Celsius, this would be at 100 degrees Celsius. Now that can be somewhat confusing, seeing all that, so let's summarize that. We can say that for reverse reactions, we use the inverse or reciprocal rule. So if we have this reaction in equilibrium and then we flip it over so it's in reverse, or written in reverse, we have KEQ1 and KEQ2 for these two different reactions. We can say that KEQ for the second reaction is the reciprocal of KEQ for the first reaction. And that would be something useful to remember. When you have multiplied reactions, we use what's called the power rule. So if we have a reaction like this, and then we multiply all of the mole values by the multiplier n, if the KEQ for the first reaction is KEQ1 and for the second reaction is KEQ2, we could say that KEQ2 is equal to KEQ1 raised to the n power. So whatever the multiplier is, that n value, that's the power to which we raise that KEQ to calculate that one. And then for net reactions, we use the sum rule. So if we can add up this reaction and this reaction to get this reaction, and notice some things are typically going to simplify out. Notice that chemical C ends up canceling out, so we don't put that in our net reaction here. Where KEQ1 is for this reaction, KEQ2 is for this reaction, and KEQ3 is for this reaction, we can say that KEQ3 is equal to the sum of KEQ2 plus KEQ1. So it's worthwhile to know the inverse rule for reversed reactions, the power rule for multiplied reactions, and the sum rule for net reactions.